think there was some error on the, so I had to cut out the previous video and I'll start over again from this part where we left off. Okay, so I forgot to apply this given fact. So if we apply that, let's plug in 0 for x. It's gonna be less than or equal to 1/2 plus c. Okay, and we know this is going to be 0. Well, this is going to equal to 0, which gives us the fact that c is going to be negative 1/2. Okay, so we can use that here. So let me rewrite that. Phi of x is less than or equal to 1/2 minus 1/2 c negative 2x. Okay. All right. So let's plug in now. Now let's plug in our boundaries. So let's plug in our leftmost boundary, which is 0 first. So if we plug in 0, that's going to be equal to 1/2. To be more exact, it's if x equals to 0, then 1/2 minus 1/2 e to the power of 0. This is 1, so this is going to be equal to 0. Our second boundary is if x approaches infinity, then 1/2 minus 1/2 e to the power of negative infinity. E to the power of negative infinity, this is going to equal to 0. It's just going to go be approaching 0. So this will equate to 1/2, because negative 1/2 times 0 will also be 0. Okay, and so this is it. This is how we have proved that the phi of x is always going to be less than 1/2 if x is greater or equal to 0, because we have shown that if x is 0, the leftmost boundary, our equation is going to equal to 0, and at most, if x approaches to infinity, then at most it's going to go up to 1/2. So our values, our y value is always bounded between 0 and 1/2. It's not going to be bigger than 1/2 or less than 0. All right, so let's move on to the next problem, which is number 3. So find a solution phi which has continuous derivative on x's between 0 and 2, and we have to satisfy these equations. All right, so I think we need to solve the equations. Let's solve the first one first. So this first given is r squared minus 1 equals to 0. And this is r plus 1 times r minus 1 equals to 0. So we get that r is positive 1 or negative 1. So r is plus minus 1, which also gives us that we can write this as c1 e to the power of 1x plus c2 e to the power of negative x. Okay. Let's look at the second equation. Let's see, which is this. So that's r squared minus 9 equals to 0. So this is the same thing as r plus 3. R minus 3 equals to 0, which gives us r is plus minus 3. So phi of x is c1 e to the power of 3x plus c2 e to the power of negative 3x. For the boundaries, it seems like we have to find the derivative. So let's do that. Differentiated once, this will be 3c1 e to the power of 3x minus 3c2 e to the power of negative 3x. And back to, and differentiated value of this is just going to be c1 minus c2 e to the power of negative x. And I think the next part is just plugging in. The first given, this is 0, so we don't have any choice but to plug it in here, because this is only true when x is between 0 and 1. Okay, so which means we're going to have to plug it into this this first equation. Plugging in 0. So that's going to be C1 plus C2, and that's going to equal to 0. For the second boundary problem, we have two choices. We're given that the differentiated value of x is 1. So it could be that our original value of x was the first case, or it could be our second case. You would just have to find one of these, because I guess we have to find a function, so one of them that applies. So let's just go ahead and use the first boundary problem, which is this. I mean, again, if we use this, we're going to get a second solution, different solution, which we can also do. But let's plug it in here. Theta 0, so that's going to be C1 minus C2. That's going to be 1. So it seems like we can add these two equations, which gives us 2, C1 equals to 1, which gives us C1 equals to 1/2. And that results C2 being equal to negative 1/2. So there you go. Our first answer, possible answer, could be that phi of x equals to 1/2 e to the power of x minus 1/2 e to the power of negative x. It's fine if you just give me this. You can also try plugging in 0 to here, to 0 to here, and then that'll give us the second set of the answer. Alright, so the last problem, I only assigned part A, but possibly I think I might assign part B for next week's homework, just because the point of problem 4 was that you guys can have a chance to read over the uniqueness proof, which is on page 58. Alright, so it's the uniqueness theorem it's theorem 4, and which is down to theorem 5. But this is just the beginning of how to do that proof, and there's not much to do for part A other than to understand that this chi is, so let's say for A, let's talk about that, chi of x0. So this, since chi is phi minus psi, this could be also written as phi of x0 minus psi of x0. And that really is it. Phi of x0 is given as alpha 1, and chi of x0 is given as alpha 2. So that's why this is alpha 1 minus alpha 2. And same thing goes here. So chi x0, this is phi of x0, minus psi of x0, and you guys can just read off the values. That's going to be beta 1 minus beta 2. So before part B, please go ahead and just revisit the readings for the Uniqueness Theorem on page 58. It goes over why we have, if we have such values such as, in this case, alpha 1 and alpha B, alpha 1, alpha 2, and also beta 1 and beta 2, why we can assume that those are the only values for any two constants, as long as this x0 is any real number, and why this is true for, or applicable for, the initial value problems. Alright, and so that was all for homework 8.